Last time in Did It Really Learn, we caught our model cheating, memorizing the training set, then falling apart on data it had never seen. We fixed it with validation and regularization. So here's the thing nobody warns you about. Every network we've built so far has been blind. It takes an image, flattens it into one long row of numbers, and asks a dense layer to make sense of it. Today we give the machine actual eyes. We're still in the same place on our pipeline, pre-process and build. But this is a deeper lab, the computer vision lab. By the end, you'll have built a convolutional network from scratch and taught it to tell cats from dogs, straight from folders of raw photos. Start with what's broken. A dense network flattens a picture. A cat's ear in the top left corner, and that same ear shifted 2 pixels right, become completely different inputs to a flat layer. It has no idea they're the same shape. Geometry, the thing that makes a cat look like a cat, gets thrown in the blender. We need a layer that respects where things are. That's the whole reason for today's lap around the loop. Same stage, pre-process and build, but instead of stacking dense layers, we're going to build a layer that looks at a neighborhood of pixels at once. Same workflow, deeper tools. Here's the key idea. A convolution is a tiny window, say 3 pixels by 3 pixels, that slides across the image. At every stop, it multiplies what it sees against a little grid of learned numbers called a filter and writes down a single score. How much does this spot look like the pattern I'm hunting for? One window sliding everywhere, hunting for one thing. And the beautiful part is what those filters learn. Nobody programs them. In the first layer, they drift toward simple edges. A horizontal line here, a diagonal there. Stack a second layer on top and it combines edges into textures. Fur, whiskers, the speckle of a nose. A third layer combines textures into parts, an ear and eye. The network builds up vision the same way you do, simple to complex. Between those layers, we do something almost rude. We throw information away. Pooling takes a little patch of the feature map and keeps only the strongest signal, shrinking the map by half. Sounds wasteful, but it's a gift. Now the network doesn't care if the ear was exactly here or 2 pixels over. It's become translation robust. The cat can wander around the frame and we still find it. There's one more trick, and it's almost cheating. We only have so many photos, and we learned last time that too little data means overfitting. So we fake more. Every time the network sees a training image, we randomly flip it, rotate it a little, zoom in a touch. The cat is still a cat, but now it's 1,000 slightly different cats, free data, and a model that refuses to memorize. Now we stack it all. Convolution pool, convolution pool, convolution pool. 3 blocks, each one seeing bigger, more abstract patterns than the last. Edges become textures, become parts, become, by the top of the stack, a whole animal. Then we flatten that rich summary and hand it to a couple of ordinary dense layers to make the final call. And the final call is just one number. We've got 2 classes, so we don't need anything fancy. One neuron with a sigmoid, squashing everything to a value between 0 and 1. Close to 0, it's a cat. Close to 1, it's a dog. That's it. One catch though, training all these filters from scratch is slow, and it needs a lot of pictures. Next time we'll learn to skip most of that work by borrowing a network that's already learned to see. But first, let's build ours. Here's the whole program, 07CNN catsdogs.py, about 3 pages. We point Keras at 2 folders of photos, build an augmentation pipeline, stack 3 convolutional blocks, train, plot the accuracy, and predict on one held out photo. Let me walk it section by section. First, the data. Image dataset from directory is the magic. You hand it a folder where each subfolder is a class, cats and dogs, and it reads the JPEGs, resizes everyone to 180 by 180, batches them, and infers the labels from the folder names. We do it twice, once for training and once for validation. and we cache and prefetch so the GPU never waits on the disk. Next, augmentation as its own little sequential model. Random flip mirrors left to right. Random rotation tilts up to 10% of a full turn. Random zoom pushes in or pulls out by 10%. We keep it as a separate block so it runs only during training. At prediction time, Keras puts these layers in inference mode and they pass the real photo through untouched. Now the network itself. It opens with that augmentation block, then a rescaling layer that divides every pixel by 255, turning 0 to 255 into a clean 0 to 1. Then the heart of it, 3 Conv2D plus max pooling 2D pairs, 32 filters, then 64, then 128. Each block seeing more abstract patterns and halving the map. Flatten, drop out to fight overfitting, a dense layer of 128, and finally that single sigmoid neuron. Compile and train, Adam Optimizer binary cross entropy because it's a 2-class problem, and we watch accuracy. Then model.fit for 15 epochs, handing it the training set and the validation set, so we can see both numbers climb. The whole history comes back so we can plot it. We plot training and validation accuracy together. The white chart you see appearing, both curves should rise. If validation flattens while training keeps climbing, that's overfitting talking, and our dropout and augmentation are there to keep that gap small. Finally, the payoff. We load one held out photo, cat.22, don't and JPG, resize it to match, add a batch dimension and call model predict. Out comes one number, below one half it's a cat, above it's a dog, and we map the folder name to a clean singular label for the printout, and there it is, 0.97, confidently a cat. And that's a convolutional network built from nothing but sliding windows and a willingness to throw information away. We took raw folders of photos and got 91% on cats versus dogs. But you might have felt the cost, 15 epochs, every filter learned from zero, and we still only just cleared 90%. Next time in Standing on Giants, we stop starting from scratch. We'll take MobileNet v2, a network that already learned to see millions of images, and bolt our cat versus dog head onto its shoulders. Same problem, a fraction of the work and a big jump in accuracy. See you there.